The ionic product of water, Kw. Water is slightly ionized according to the following equation. So that means it exists in an equilibrium where it forms H plus ions and OH minus ions in aqueous solution. Position of equilibrium, however, lies very much to the left. Now, as water is in equilibrium, an expression for Kc can be given. We've covered Kc previously. That's the equilibrium constant, where you do the concentration of the products divided by the concentration of reactants. And again, something we previously mentioned, that when the concentration of one of the substance is so much greater than that of the others, so in the case of water, the concentration of water is much greater than that of the H plus ions and the OH minus ions, it does mean that the concentration of H2O is effectively constant. So that's what we've written there. The concentration of H2O is much greater than that of the H plus and OH minus ions, meaning the concentration of H2O is effectively constant. And we can therefore incorporate it into the equilibrium constant Kc to create a new constant known as Kw, which is the ionic product of water. And at 298 Kelvin, the ionic product of water, Kw, equals exactly 1.0 times 10 to the minus 14. And this value here is something you'll need to know off by heart. So here I've written that in pure water, each water molecule that dissociates split into one hydrogen ion and one hydroxide ion. So we can therefore say that the concentration of H plus ions is equal to the concentration of OH minus ions. And then based on the value of Kw at 298 Kelvin, if we rewrite the ionic product of water equation, sub in that value, which was 1.0 times 10 to the minus 14, we can therefore write, because these two equal the same, that it equals H plus squared. So if we square root, we'll find the concentration of H plus ions as being 1.0 times 10 to the minus 7. And then taking a previous equation we've looked at to find the pH of pure water at again 298 Kelvin, we take our pH equation, we sub in that concentration of H plus ions we just found, and sure enough, as you might expect, the pH of pure water is 7.00. Remember, we give pHs to 2 decimal places, which makes sense as we know that water is neutral. Now, one thing to be aware of is that the dissociation of water into its ions is an endothermic reaction, so delta H is positive, and what that therefore means is that if you were to increase the temperature, it favours the forward reaction, so the position of equilibrium shifts to the right, and what that has a knock-on effect is meaning that the value of that ionic product of water, Kw, increases due to the increased concentration of H plus ions and hydroxide ions. So if we look at another example, the value of Kw at a higher temperature of 323 Kelvin is, as you'd expect, higher at 5.48 times 10 to the minus 14. Let's write the ionic product of water equation. Sub in 5.48. We know that it equals H plus squared, square root to find the concentration of H plus ions, and then find the pH. So we can see here that the pH has decreased slightly. The odd thing here, though, is that despite the fact the pH has decreased, pure water we still count as being neutral because the concentration of H plus ions equals the concentration of hydroxide ions. So combining several different steps, so using Kw to calculate the pH of a strong base. Strong bases completely ionize in water according to this equation, therefore the concentration of a strong monoprotic base is the same as the concentration of hydroxide ions. So being asked to calculate the pH of a 0.1 mole per dm cubed sodium hydroxide solution at 298 Kelvin. So the first thing remember is that because sodium hydroxide is a strong base, it means it fully dissociates. So you can therefore say that the concentration of sodium hydroxide equals the concentration of hydroxide ions. So in this case, that tells us that the concentration of hydroxide ions is 0.1. Let's now find the concentration of H plus ions because after all we need that to feed into the pH equation. So the way we do that is by writing Kw equals, we said that we need to learn the value of Kw at 298 Kelvin. Remember I said it's always 1.0 times 10 to the minus 14. The concentration of hydroxide ions we know is 0.1. So solve for the concentration of H plus ions by dividing both sides by 0.1 to get a concentration of 1.0 times 10 to the minus 13. And now to find the pH. So our pH here is 13.00. That makes total sense. We started with sodium hydroxide. Sodium hydroxide is a strong base, so it makes sense, therefore, that it has a high pH. So what did we do to calculate the pH of a strong base? We knew, first of all, that the concentration of hydroxide ions equals the concentration of sodium hydroxide because it's a strong monoprotic base. We wrote down the ionic product of water equation, subbing in our value of Kw at 298 Kelvin. That enabled us to find the concentration of H plus ions, and then we fed that directly into our pH equation. So in our second example, we're being asked to calculate the pH of 0.0120 mole per dm cubed solution of calcium hydroxide at 298 Kelvin. So straight away, look, this is the formula of calcium hydroxide. It's diprotic, which means it releases 2 lots of hydroxide ions. In order to find the concentration of hydroxide ions, therefore, we'll need to do 2 lots of that. Let's write down our ionic product of water equation. Remember, we've learned that number off by heart. Solve for H plus ion concentration. Now let's find our pH. And as you'd expect, it's another strong base. Our pH is 12.38.